Welcome back to TechTide Digital Lifestyle, and this is tutorial lecture series 3 of our Alternator Masterclass. In today's session we move from physical construction into actual electrical operation, which is where most examination questions and onboard troubleshooting scenarios are based. We will clearly understand how an alternator generates AC voltage using electromagnetic induction, how the rotating magnetic field is created, how the EMF equation is derived and applied, how frequency depends on speed and number of poles, and finally how three-phase voltage is produced. These principles are essential for synchronization, voltage control, and stable marine power systems, so watch carefully till the end. Before starting this lecture, like this video and subscribe my channel TechTide Digital Lifestyle. Electromagnetic induction. The fundamental law behind alternator operation is Faraday's law of electromagnetic induction. This law states that whenever the magnetic flux linking a conductor changes, an electromotive force is induced in that conductor. In an alternator, this flux change occurs because the magnetic field produced by the rotor sweeps past stationary stator conductors. Mechanical energy supplied by the diesel engine or turbine is converted into electrical energy through this electromagnetic interaction. Always remember for exams, no relative motion between magnetic field and conductor means no voltage generation, which is a very common Viva question. Rotating magnetic field. When DC current flows through the rotor field winding, it produces north and south magnetic poles on the rotor surface. As the prime mover rotates the shaft, these poles rotate mechanically, creating a rotating magnetic field inside the stator bore. The flux lines shown in the graphic illustrate how this magnetic field sweeps across the stator conductors continuously. The speed of this rotating field is exactly equal to the rotor speed, and this determines the frequency of the generated voltage. Understanding rotating magnetic field theory is extremely important when studying synchronous machines and parallel operation. AC waveform generation. As the rotor poles pass over a stator coil, the magnetic flux linking that coil varies continuously from maximum to zero and then to maximum in the opposite direction. Because induced voltage depends on the rate of change of flux, the output follows a sinusoidal waveform. When flux is maximum, the rate of change is zero, so voltage is zero. When flux changes rapidly, voltage reaches a peak value. One complete north-south pole passage produces one electrical cycle. This graphical relationship between rotor position and sine wave is very important in theory exams and helps visualize how alternating current is produced inside the machine. EMF equation. From theoretical analysis, the generated EMF per phase of an alternator is given by the equation E equals 4.44 multiplied by frequency, flux per pole, number of turns per phase, and the winding factors, which include distribution factor and pitch factor. This equation clearly shows that voltage depends on magnetic flux, speed, and winding design. Increasing excitation increases flux and therefore voltage, while reducing speed lowers frequency. For ETO candidates and marine engineers, this equation explains why voltage collapses when excitation fails or why abnormal frequency occurs when engine speed is unstable. Speed-frequency relationship. The frequency of generated voltage is related to rotor speed and number of poles by the formula F equals P multiplied by N divided by 120. This is called the synchronous speed relationship. For example, a 4-pole alternator running at 1500 RPM produces 50 Hz supply, which is commonly used in marine systems. A 6-pole machine would need to run at 1000 RPM to produce the same frequency. Engineers must remember this relationship during synchronization, because mismatched frequency will cause serious electrical and mechanical stresses when connecting generators to a live busbar. Three-phase generation. Most alternators are designed to produce three-phase supply because it is more efficient and suitable for driving motors and heavy loads. Three identical stator windings are placed around the stator core with 120 electrical degrees separation. As the rotating magnetic field sweeps past them, three sinusoidal voltages are induced that are equal in magnitude but displaced in phase. This balanced three-phase system allows smooth torque production in motors, reduced conductor size for transmission, and stable shipboard distribution. The windings may be connected in star or delta depending on voltage level and neutral grounding requirements. Voltage control by excitation. The magnitude of alternator voltage is controlled by regulating the DC field current in the rotor through the excitation system and AVR. When electrical load increases, terminal voltage tends to fall, and the AVR automatically increases excitation to strengthen the magnetic field and restore voltage. When load decreases, excitation is reduced. This control also determines reactive power sharing between generators running in parallel. Marine engineers frequently monitor excitation current and AVR alarms because problems in this system can lead to voltage instability, blackout situations, or incorrect load sharing between diesel generators. Marine DG set example. In a typical marine diesel generator set, the diesel engine provides mechanical input to the alternator, and its speed is regulated by an electronic governor to maintain constant frequency. At the same time, the AVR regulates excitation to keep voltage constant. The electrical output flows to the main switchboard, from where power is distributed to pumps, compressors, cargo gear, and hotel services. When a large motor starts, the load suddenly increases, causing momentary speed and voltage dips, but the governor and AVR respond quickly to restore normal operating conditions. This coordinated action ensures stable shipboard electrical systems. Summary or exam focus. To conclude today's lecture, alternators operate on electromagnetic induction where a rotating magnetic field cuts stator conductors to generate AC voltage. The EMF equation links voltage to flux, frequency, and winding design, while the frequency formula connects rotor speed and number of poles. Three-phase systems dominate marine power distribution because of their efficiency and stability, and excitation control maintains voltage during load changes. For examinations, we ready to derive equations, sketch waveforms, explain synchronous speed, and discuss DG set operation practically. If you found this lecture useful, like the video, subscribe to TechTide Digital Lifestyle, and comment your profession and country below. I'll see you in the next tutorial on excitation systems and AVR. Thanks for watching this tutorial on TechTide Digital Lifestyle. If this video helped you understand alternator working principles, EMF equation, and three-phase generation, please hit the like button, subscribe to the channel, and turn on the notification bell so you never miss our upcoming marine and industrial electrical lectures. Drop a comment below telling us your profession, ETO, marine engineer, student, or industrial electrician, and what topic you want us to cover next. In the next video we dive deep into excitation systems and AVR control, which is extremely important for shipboard generators and exams, so make sure you stay connected with TechTide Digital Lifestyle and keep upgrading your engineering skills.